General relativity, step by step. I spent some considerable time talking about the Q of R term in our metric, and now I'm going to talk about the A of t, the expansion term. Right, so let's start out with our metric, ds squared. Actually, I'll pinch in a bit. ds squared equals minus dt squared plus A of t squared times dr squared plus Q of R squared, that's supposed to be a plus, times d theta squared plus sine squared theta d phi squared. There we go. So we've been looking at that metric for quite a long time. I'm going to consider only radial motion now, which means that these terms here disappear because I've got no angular dependence. So I guess if that's my origin, I'm considering only radial motions here with no angular component at all. Now I hasten to add that it looks like, well, I have singled out a particular point so in the universe, so it looks like I've broken the universal homogeneity assumption which I made earlier, but I haven't, because I could have singled out any point in the universe for this radial motion to be defined. It's like singling out the North Pole on the surface of a sphere. Yes, that is a singular point of your coordinate system, but it doesn't mean that anything peculiar happens when you walk over the North Pole. It still looks like a flat plane to you. It doesn't. If you're walking around on the North Pole, it looks just the same as any other part of the Earth. Okay, so what have I got? I've got that ds squared equals minus dt squared plus A of t squared dr squared. This thing here being Hubble expansion. And so that means, of course, that the simplest thing to consider is light, I guess radial light as well, for which, of course, ds squared equals 0. I just want to make, I know it's obvious, but I feel I ought to say it, that we've got this beautiful metric that works for the whole cosmos, but it also works for small-scale processes like light and photons being emitted. And this is why it works, because we can link small-scale processes to large-scale evolution of the universe. So for radial light, we've got ds squared equals 0, and that means, of course, that dt squared equals A of t squared times dr squared. And so that means that dt by dr equals plus or minus A of t. And I guess we could also invert it and say that dr by dt equals plus or minus 1 over A of t if we wanted for radial light. So what does that look like? I'm going to draw this. Let me just pinch in a little bit. I'm going to draw a nice set of coordinates. That's r and that's t. And in orange, I'm going to draw my world line. That's me. And I'm sitting here at r equals 0, let's say. And there's another galaxy here who I will draw in yellow. Now, at this point, I'm going to reveal that I casually drew it vertically. And you might expect it to do that because the universe is expanding. As time goes by, you'd expect the galaxy to get further away, which it does. But not in this diagram. In this diagram, the world line is vertical because this r here is co-moving r. So by construction, all my observers, all my galaxies have got constant r. And I guess I could draw other galaxies as well in different colours, and they would all have a vertical world line as well. Okay, so what I'm going to do now is I'm going to choose an instant of time, and at this point here, actually I'll draw Mr. Yellow Galaxy a bit closer. I'll draw him a bit closer. I'll draw him there. And what he's going to do, he's going to emit a photon. This is t emit, time emitting, and this guy's going to draw a photon. Now, because of this rule here, we've got that dt by dr equals plus or minus A of t. And so what I'm going to do is I'm going to choose A of t emit to be equal to 1, just by choice of unit. And so what that means is that the slope, I'll do it in red, the slope of this line is 45 degrees here. But as time goes by, because the universe is expanding, A of t is increasing. So how can I write that down? I can say A of t is increasing. And so what that means is that the world line for this photon will get steeper and steeper and steeper. I can't draw it very well. I'll try that again. It gets steeper and steeper and steeper as time goes by. Simply because dt by dr equals plus or minus A of t. I guess the other route, the plus or minus corresponds to going in and out. The other route, if I go back to red, would correspond to him sending a photon away from me. And I guess these guys could send photons away as well if they really wanted. Or they could send them that way if they wanted. Do what you like. Now what I'm going to do is I'm going to draw another time. I'm going to draw it quite close. And I'm going to see what happens to photons here. I'm going to pinch in a little bit and see if I can draw it a bit better this time. So here, remember that time is a universal coordinate because my t, oops, that's red, because my t is proper time for all my observers, and everybody agrees on that. So it doesn't start at 45 degrees, it starts steeper than 45 degrees because it's starting at the same slope here. So it's actually moving steeper than that here and continues to get steeper and steeper and steeper. I'll get rid of that. And steeper and steeper and steeper. And so there's a mismatch between this time here and this time here. And that is the origin of the cosmological redshift. Let me just spend a little bit of time talking about this. Yeah, in this guy here on the yellow galaxy here, he waits for a little bit of time. He waits for 1 second between sending these pulses out, but I have to wait, it looks like about 2 seconds for those pulses to get to me. So if you take these two events here being the crest of a wave, the wave of an electromagnetic ray coming towards me, well, I've got to wait longer between my rays, and so it will look red-shifted. And that is the origin of the cosmological redshift. And I'll talk about that properly in the next screencast. Stop.